Students, in last two videos we had discussed about the structural change and economic growth. So by structural change we meant the change in composition of output. So for example, the share of agriculture falling while the share of industry and services increasing, and the same as reflected in the shift in labor force from agriculture to industry and to services. So these structural changes in the process of economic growth we discussed in the earlier lectures from the demand side perspective and supply side perspective. So today we will be discussing about structural transformation in the process of economic growth. By structural transformation, what we mean, it is change in the organization and efficiency of production accompanying the process of development. See how the productivity of sectors change, and in that process how there is a shift in the importance of one sector vis-a-vis another sector. Particularly we will discuss this in the context of agricultural productivity and industrialization. We will discuss how higher agricultural productivity promotes industrialization in the process of economic growth. This again in a unified framework or integrated framework which we have been using for discussing growth theories, particularly the neoclassical and endogenous growth theories. So if you look at the history of economic progress, basically the industrialization which started in Britain in some 200 years before, that rapidly spread to some of the countries which are today the club of OECD countries. But this industrialization could not reach many countries in Asia, even Eastern Europe, Africa, etc. So there are various perspectives why industrialization or industrial revolution happened in Britain and how it spread to some countries and not to others. But one very popular perspective, which is basically due to Knox 1958, Rostow 1960, Overton 1996, is the productivity of agricultural sector playing a role in the process of industrialization. Basically, it is hypothesized that if the industrial sector is having high productivity, then there is surplus labor in agriculture. No, I think if agricultural sector is highly productive, the productivity is high, then there will be surplus labor in agricultural sector, and there is a possibility or opportunity of shifting this surplus labor from agriculture to industry, and that facilitates the industrialization process. So basically in this line we'll be discussing the model due to Matsuyama 1992, and the reference for this lecture is the book Introduction to Modern Economic Growth by Daron Acemoglu, 2009. Okay, so in this book, in chapter 20, we are discussing about economic growth and development, and there we are discussing about this structural transformation, particularly the link between agricultural productivity and industrialization. So first I will basically discuss the basic features of the model, and then we will go to the discussion on the equilibrium, which will help us understand how with high agricultural productivity industrialization takes place, and in the overall process of economic growth as explained in the neoclassical and endogenous growth theories. So basically this model has two basic characteristics about which we have discussed in earlier topics. One is the demand side explanation of structural change due to Engel's law. So Engel's law, which we discussed earlier in the context of structural change and economic growth, we discussed that as income grows, people spend a lesser share on food items. Okay, so this is one idea which will be using, which is used behind this model. And secondly, the idea of Romer that learning by doing externalities in the production process, which helps technological progress. Okay. So these two ideas are basically the underlying sort of insight behind this model. So this model has some 7 to 8 characters which I need to explain. First is the economy is in continuous time. So the household, farms, they are living for infinite time horizon and in a continuous time. Secondly, the population is normalized to 1. Okay. So then once we are normalizing to 1, we will talk about the fraction of population employed in agriculture, fraction of employment engaged in industry, etc. The preference of the household is same as we have been discussing in many of our growth models discussed in the course. So it is the preference of the infinite living representative household, which is given by U. You are familiar with this production function, where U is utility, and it is basically integration from 0 to infinite of Ct e to power minus rho t dt. Here basically the rho is the coefficient of preference. So a higher rho implies the higher preference for current consumption over the future consumption. So let me explain. So basically imagine this household living for infinite years. Okay, so he is consuming in the current year, next year, subsequent years, like this. So this is basically some sort of is a continuous time, and if had it been discontinuous time, it would have been sum of those consumption expenditures of the household. Okay, so in continuous time we are using integration, and e to power minus rho t basically capturing the preference for current consumption over the future years consumption. Now as we discussed in the model for structural change and economic growth from the demand side perspective, here the consumption basket of the individual, it consists of 2 types of goods, agricultural good and manufacturing good. Okay, so in the previous model we had agriculture, manufacturing and services. So compared to that, this is simpler. Here basically the consumption aggregator is given by this Ct is equal to CAT minus lambda A whole raised to power alpha, and then CMT raised to power 1 minus alpha. So basically here lambda A is the subsistence level of consumption expenditure, subsistence level of consumption of food items or agricultural items. So this consumption aggregator is using the consumption of agriculture item in a complicated way, and for the manufacturing good it is relatively simpler, and the exponent alpha or 1 minus alpha basically signifies the importance of agricultural product vis-a-vis consumption of agricultural product vis-a-vis manufacturing product. So now of course alpha varies between 0 and 1. Now the fourth assumption or characteristic of this model is a closed model. So there is no foreign trade in this. So once we are closing the model, then consumption will be equal to production. Okay, so this holds for both the sectors. For the agricultural good, production is equal to consumption. For the manufacturing good also, production is equal to consumption. Now let us come to the production function. The fifth item for us is in the model, the production function. So the production functions of agricultural good and manufacturing goods are treated differently here. So basically the production function for the manufacturing good is xt times f, okay, and this is basically taken as explicit function of labor. LM stands for labor employed in the manufacturing sector. xt is the technology, okay. So the output of manufacturing sector is given by this production function, and while for the agriculture it is little different. You have a total factor productivity factor which is BA and is a function of GLA. So basically what we observe here, we observe that the manufacturing sector, in the manufacturing sector, in the production function, there is a technological progress. So xt is appearing explicitly, and this xt, the technology of production, this following Romar's learning by doing model, it is a function of the amount of production of agricultural good. Okay, so basically we can represent this in the form of this equation, where xt dot, which is change in technology, is equal to beta into ymt. So where beta measures the extent of this learning by doing effect. Okay, so beta is greater than 0. So if the output of manufacturing sector improves, that helps in rapid technological progress. On the other hand, the production function of agricultural good, we are assuming there is no technological progress in that, but there is a factor BA, which is basically the productivity of agricultural sector, and this productivity may be due to the technological progress of the past, or may be due to the quality of land. More fertile the land, then the BA is higher. Okay, so then one more thing about this production function is both the production function for manufacturing sector as well as that for the agricultural sector, they are subject to diminishing return to labor. Okay, so this implies there are other factors of production. Say for example, for agriculture there may be land, there may be some other factor of production, maybe capital. Similarly for the manufacturing sector, there could be other factors of production which are not explicitly considered in this production function. So that's how the both the production functions are subject to diminishing return to labor. Okay, and then certain characteristics of this both the production function are similar to the neoclassical production function otherwise, other than constant return to scale. So basically your f0 is equal to 0, similarly g0 is equal to 0, then first order partial derivative of both the production function is equal to 0, whereas second order derivatives for both are negative. Okay, so this is about the production functions. Then let us next come to the market clearing conditions. So basically the labor market clearing condition is given by LMT plus LAT is equal to 1, because we assume we normalize the population to 1. So the the fraction of workforce working in the agricultural sector and factor plus fraction of the workforce working in the manufacturing sector equal to 1. Now if we assume NT is the fraction of the workforce working in industry, then of course then 1 minus NT is the fraction of the workforce working in agriculture. So that way we can now redefine LM. LMT is equal to NT, LAT is equal to 1 minus NT. So now in place of LMT and LAT in the production functions, we can replace these two by NT and 1 minus NT. Then from the profit maximizing functions, we can derive these equations. WT is equal to BA and G prime 1 minus NT. So here LA is replaced by 1 minus NT, and for the manufacturing sector, WT, W stands for wage, equilibrium wage. So equilibrium wage is here PT into XT F prime NT. Why P is not appearing here? Because we are assuming the price of the agricultural good as numerator, so it is equal to 1. So then price of the manufacturing good, that is the relative price, is PT. So this way we can have from the profit maximizing function we can get the equilibrium values of WT for both the sector, and for the market clear, the W equilibrium W has to be same both in the agricultural sector as well as in the manufacturing sector. So using that we will derive this equation. So basically this equal to this. So here it is representing VA G prime 1 minus NT is equal to PT into XT F prime NT. So let us denote this as equation 3. And now the next condition for us is we assume that agricultural productivity is high enough to meet the minimum agricultural consumption requirement or subsistence level of consumption for agricultural good, which we denoted as lambda A in the consumption aggregator. So here basically this condition is mathematical put that way. So BAG, this is basically the production of agricultural good, should be more than lambda A, which is basically the subsistence level of consumption, and which is greater than 0 in ton. And the budget constraints, of course, we can define for the household. The household has two sources of income. One is wage, and the other is profit from the production. So, and there are two expenditures. One expenditure is expenditure on the consumption agricultural good, another is expenditure on the manufactured good. So this budget constant can be given this way: CAT plus PT into CMT. This is expenditure on the agricultural good, this is expenditure on the consumption expenditure of the manufacturing good. So this should be less than equal to total income, which is WT and phi t. Okay. So this is about the characteristics of the model or specification of the model. Now once we specify the model, from this we can derive the equilibrium conditions. So like we did earlier in our previous growth models, so the equilibrium in this economy is defined as the path of consumption of agricultural good, manufacturing good, and allocation of labor between the two sectors, that is agricultural sector and manufacturing sector, so that households utility is maximized and farms profit is maximized and all goods and factor markets clear. Okay, so this way we will define equilibrium as path of these variables like consumption, factor allocation, etc., which are derived from the profit maximization and utility maximization function of the respective players. Okay, so from the utility maximization function we can derive this equation, which is CAT is equal to lambda A plus alpha times PT CMT whole divided by 1 minus alpha. So basically how we can do this, the consumption aggregator, you can basically undertake a logarithmic transformation. Once you are undertaking logarithmic transformation, then from the utility maximization function we can derive this. Okay. Now secondly, we have assumed that the economy is a closed economy. So once we assume the economy is a closed economy, so then consumption is equal to production for both the sector. So CA is equal to YA, which is equal to BA 1 minus BAG 1 minus NT. Okay, this is basically the production function we defined earlier. Similarly, CMT is equal to YMT, consumption of manufacturing good is equal to production of manufacturing good, and this is the production function for the manufacturing good. Okay, so now let us put this system as system 5. Now if you combine 3, 4, 5, from that we can derive the equilibrium condition. Okay, so basically what I'll do, this CT and CM here, okay, these two in terms of this right hand side terms will basically substitute here. Basically, in place of CAT, let us substitute BAG1 minus NT. Similarly, in place of CMT, let us substitute CMT from here in this equation 4 by XTFNT. Okay, then bring PT from equation 3. So from equation 3, I can express PT as this term divided by this term. Okay, so that way we'll replace PT in equation 4. Then once you do that, then we'll get this term, which is G1 minus N. In fact, I'm not for simplicity I'm not included T here. So G1 minus N minus alpha G prime 1 minus N Fn whole divided by 1 minus alpha F prime N is equal to lambda A over BA. Okay, this basically you will get after substituting the values of CA, CM and PT in equation 4. Equation 4 will give you this. Okay, now this part, the left hand side, let us denote this left hand side as psi NT. Okay, psi NT. So what we will observe here, the psi NT is strictly decreasing. Okay, so here you will see that if N is increasing, then the relative output of manufacturing sector as compared to relative output of agriculture sector will increase. Okay, so this we are directly getting from this left hand side of equation 6, because it is a strictly decreasing function. Okay, now what we can do by solving equation 6, we will get that equilibrium value of N, which will denote as N star, which satisfies equation 6. So then I can basically which satisfies either 6 or 7. So I'll get equilibrium value of N star, which is lambda A over BA. Now from this I can derive the inverse function. The inverse function of psi A, which I can define N star as inverse of lambda A over BA. Now this equation gives us the basically main intuition behind this model. So the implication is, if BA is increasing, if BA is high, BA is what? BA is productivity of agriculture sector. If BA is high, N star will be high. So what is N star? N star is here the fraction of labor force working in manufacturing sector. Okay, so if BA is high, N star being a increasing function in BA. Okay, so when BA is high, N star is high. So once N star is high, the output of manufacturing sector will be high. If you look at the production function, the manufacturing sector production function is XTFN, right? So with high N star, our YMT will be high. So industrial output will be high. Now that will again give to the feedback, which will lead to technological progress in the manufacturing sector, because the change in technology XT dot, which we define, it is beta YM, right? So let me repeat again. For high BA, that is high agricultural productivity, N star is high. If N star is high, YM is high, that is the output of manufacturing sector is high. Now if manufacturing sector output is high, through the relation of change in technology with manufacturing sector output, there will be faster technological progress. Okay, the learning by doing effect, which we are assuming following Romar. So again, the faster technological progress will lead to higher output of the manufacturing sector, because from the production function, Ym is X3 multiplied by the F, okay, the Fn. So in this process, higher agricultural productivity will lead to higher N star, higher fraction. Basically, because as we discussed in the beginning, because agricultural productivity is high, there is surplus labor in agriculture which can shift to industry. So the fraction of workforce in industry will increase. N star is high. So once N star is high, from the production function, output of manufacturing sector will be high. That will lead to faster technological progress, and this faster technological progress will feed in for higher industrial output continuously. Okay, so because at each stage, once industrial output is high, that will lead to higher technological progress, and this will continue perpetually. Okay, so this way, within the similar framework of the growth theories which we have discussed earlier, we can say that in the process of economic growth, there will be technological transformation. Okay, and so this technological transformation we are explaining in terms of how higher agricultural productivity is leading to the industrialization process. Okay, so thank you.